This is the first video on section 5.3 on partial derivatives. Now, a lot of what we do in Calculus 3 is very similar to things we've done in Calculus 1 and Calculus 2. In section 5.2, we looked at limits, and we did a lot with the epsilon delta definition of limit, and that's why I'm guessing that you probably didn't particularly like section 5.2 that well. But that's also the reason that I'm guessing you will like section 5.3. So in section 5.3, we're going to take another look at derivatives. Now, partial derivatives aren't exactly the same as the derivatives that you learned in Calculus 1 and Calculus 2, but they're similar enough that I think you're going to be very comfortable with this. So we have z is f of xy, so f is a function of two variables. And so we have something called the partial derivative of f with respect to x. And so we have this partial symbol too. So we have partial of z over partial x. This is similar to the Leibniz notation you saw for the derivative dy over dx. And so this is the limit as h goes to 0 of f of x plus h, comma, y minus f of xy divided by h. And of course, provided the limit exists. I put that in the notes, but I didn't write that here. But of course, every time you define something in terms of a limit, you have to say provided the limit exists. And the partial derivative with respect to y, again, we have this, I have a typo there. Oops. So this should be partial with respect to y, not x. So again, I hope you're actually going to watch the whole video and not just the first frame, because there was a typo here. The partial derivative of z with respect to y. So we have this partial. This is the limit as h goes to 0 of f of x, comma, y plus h minus f of xy divided by h. Now, what these are, this is the rate of change of x if you're holding y constant. This is the rate of change of y when you're holding x constant. That's what these are. So we sort of think of f of xy as a function of x. You hold y constant and then you think of it as a function of x when we calculate this. And here we sort of think of f as a function of y. We take our f of xy, but we hold x as a constant, and we think of y as our variable. And then we calculate the rate of change of that variable. And so in Calculus 1, something that we discovered is that polynomials were very easy to differentiate. And so in Calculus 3, polynomials are fairly easy to find the partial derivatives of. And so let's look at example 137. So we have this polynomial. It's a function of x and y. We're going to take the partial derivative with respect to x. Now, as we take these derivatives, the thing to keep in mind is you're not using the product rule with x and y. You're considering y as a constant. So you're just pretending y is a constant, and you're going to treat it like a constant as we take the partial derivative with respect to x. So we just use the power rule. So we have 12x squared y squared. Then we have 2 times negative 12. We have negative 24x y to the fourth. The derivative of x is 1. The derivative of 2y is 0. Remember, we're treating y like a constant. All the way through, the y squared stayed the y squared, the y to the fourth stayed the y to the fourth. The partial derivative with respect to x of 2y is 0 because we're treating y like a constant. To find the partial derivative with respect to y, we treat x like a constant and y like the variable. And so we have 2 times 4, so we have 8x cubed. It decreased the exponent by 1. Then we have 4 times negative 12, so negative 48x squared y cubed. The partial derivative with respect to y of x is 0, and the partial derivative with respect to y of 2y is 2. So what we have done is we came through here, and we pretended x was a constant. We treated x like a constant and y like the variable. We did not use a product rule. Okay, we're not thinking of y as a function of x. We're not thinking of both of these as variables as we do this. We pretend one of them is a constant. For example, 138, we have a rational function. We have a polynomial divided by a polynomial. So we use the quotient rule through here. So we take the partial derivative with respect to x of the numerator. Remember, we're just treating y like a constant. And so we multiply the partial derivative of the numerator times the denominator minus the numerator times the partial derivative with respect to x of the denominator, which is 2x. Remember, we are considering x and y as constants. Excuse me a moment.